if I asked you to predict the solubility of an ionic compound, such as barium carbonate, what I'm really asking is what happens when you put this thing in water? Does it dissociate into its ions? Does it remain held together by its ionic bond? Think about it like a tug of war. A water molecule is a polar compound. It's got a positive end and a negative end. If you put something that is ionic into water, that means you're adding another substance that has a positive end and a negative end. That's like putting a magnetic substance into a magnetic solvent. Both have positive and negative poles. The way the water dissolves the ionic substance is because of the attraction between the poles of the water and the poles of the ionic compound. The negative pole of water attracts the cation, and the positive pole of water attracts the anion. In this way, as long as the pull of water's poles is stronger than the ionic bond that holds the cation to the anion, the water will be able to separate the two halves of the ionic compound. Let's take a look at your solubility table that we looked at in Chapter 3. Remember, this is something from page 126. We obviously haven't looked at it in a while. Okay, here's your solubility table. Let's take a look at some of the similarities and differences between the soluble compounds and the insoluble compounds. Okay. So if we look at this, we can see that our insoluble compounds are all listed over here. Okay. And it does have a few exceptions. You also have some compounds that are definitely insoluble, but of course those have some exceptions as well. So let's look at this. If we look at all of our soluble compounds, many of them have either a +1 or a -1 charge. Okay. There are some exceptions to that. You can see that the sulfate down here has a -2 charge. But for the most part, all of our compounds that are soluble have really low charges. Okay. We do have some exceptions over here. Many of those exceptions, as you can see, have +2 charges, so their charges are a little bit greater. But if you look down to the section where most things are insoluble, you'll see that a lot of these charges really are on the bigger side, -2, -3. Okay? And the exceptions are really just the ones that have been talked about previously up in the soluble section. Hopefully this is sort of reminding you of Coulomb's law, or at the very least it's making you think about the number of electrons that are shared or transferred in an ionic bond and how strong that bond might be and how hard it would be to break. Okay, here's Coulomb's law, just a little refresher from Chapter 3. Okay. If you look at Coulomb's law, it expresses how the force of attraction between two ions, the cation and the anion, has to do with the charge of the ions and the distance between them. And then K, of course, is just a constant. Okay. So if we go back to our solubility table, let's go back to that real quick. We can see that the ions that have the larger charges, okay, go over to Coulomb's law, are going to have bigger numbers here, which is going to indicate an overall bigger force of attraction between the ions. Overall, that's going to make it harder for those ions to dissolve in water. The attraction of the water molecule's poles to the different ions in an ionic compound with high charges may not be enough to pull the ionic compound apart and thus dissolve it. I'd also like to consider the strong electrolyte, weak electrolyte discussions we've been having regarding acids and bases. Remember, a strong electrolyte is one that dissociates 100% in water. It's strong because it gives the most amount of ions to the solution. A weak electrolyte contributes fewer electrolytes. In fact, weak electrolytes may only dissociate a small amount and may instead remain in their original solid ionic crystal state. With acids and bases, this means that a strong acid and a strong base do not really have a K value or really participate in equilibrium. The charts list their K values as simply large because they are so product favored. They dissociate so much. With weak acids and bases, we found that we not only had to worry about neutralization reactions, but we also had to worry about a state of equilibrium because the weak acids and bases exist in water in a state of dynamic equilibrium, constantly dissociating and then reforming their original compounds. All of these concepts come together so that we can add a more accurate and more quantitative assessment to our discussion of solubility of ionic compounds. Okay? Where we formerly, in previous chapters, just used our solubility table, we're going to add a little bit more to that, add a little bit more depth. Okay? Both the weak electrolyte ones and the strong electrolyte ones. The information that is summarized in your solubility table, which I hope you've memorized, okay, is important. So we're not totally getting rid of that. But I want to give you some background information to it and make it a little bit more versatile for you. So let's take a look at that dissociation reaction for the barium carbonate that I mentioned before. Okay, so here we have our barium carbonate. We have it shown dissociating from a solid state here into an aqueous state. It's 2 ions. Okay, this particular reaction is balanced just the way it is. Notice that the ions both have a numerical value to their charge of 2, which, as we said, according to Coulomb's law, would suggest that their attraction to each other is very strong. If we were to write a law of mass action for this dissociation reaction, it would look like this. Because if you remember, we never include our solids. Those don't get included in our law of mass action. So the only things that will be included are our aqueous compounds, and in this case, they're both products. And that's really going to be the case for any KSP problem. All right, so that's our law of mass action that we would wind up for this. This would suggest that a very large value of K would tell us that we have a very product-favored reaction, okay, because the entire law of mass action is dependent on those 2 ionic products. Okay, so a large value of K means that this thing's dissociated a lot. Okay, it's probably a strong electrolyte. A small value of K would tell us that this compound dissociates very little, okay, meaning the small K number would come from not having a lot of this or a lot of that, which means this reaction just didn't happen that much. Okay. This is probably a weak electrolyte. The K value that we use directly applies to this concept is called the solubility product constant, because it's always calculated using the product of the concentrations of the ions of the solution. Just like this, we're using the ions of the solid to calculate our KSP, their concentrations. The way of writing this is using a KSP. Okay, and here's a quick summary of what I just said. So let's get back to our problem. If you look in the back of your textbook in Appendix J, you'll find that there's a table that lists the KSP values for a variety of substances, including barium carbonate. It gives the value of the KSP for barium carbonate as being 2.6 times 10 to the minus 9th. You may not know a ton about how to assess this number, but hopefully, if you compare it to the K values we've been working with, hopefully it looks like a pretty small number to you. This should not be a surprise, because if I'd asked you to assess the solubility of barium carbonate before we started this equilibrium unit, you would have looked at your solubility table, and hopefully you would have seen that barium carbonate, just like all other carbonates, is listed as insoluble. Therefore, a really reactant-favored reaction, a very small KSP type of reaction, is what we would have expected. At this time, though, it's important to draw a difference between KSP and solubility. They are very related, as you can see. You can even use one to calculate the other. However, the solubility of a salt is the quantity present in some volume of a saturated solution. It's expressed in moles per liter, grams per 100 milliliters, or some other unit such as that. It's the how much. The solubility product constant, the KSP, is a constant for a given temperature that describes the state of equilibrium that exists for an ionic solid in water. Okay, so it's a constant as opposed to just some description of how much stuff is in a given sample. Solubility problems generally come in 2 types. You can either be asked to calculate the value of KSP or calculate the solubility from a KSP. So let's take a quick look at both of these types. First, for our first problem, we're going to look at the solubility of copper bromide. Okay. So we're given a solubility of copper bromide, and you can see that this one's expressed in moles per liter at 25 degrees Celsius. So to start with, it's important to have the law of mass action, and I have that written down here. Okay. As you can see, I did not include the solid, which is up here, because we never do. And so therefore, the KSP, our solubility product constant, is the product of our two ion concentrations. All right, so let's start off by doing an icebox. I'm going to write IC here on the side. Again, we're going to totally ignore our solid because it doesn't really participate in our solubility product law of mass action. We're going to start off with zeros for our initial concentrations. We're going to have a change of x, which is going to give us x and x, which really gives us a KSP equation, a law of mass action, of x times x. If we translate what we have down here up to here with our equilibrium x's put in. Now if we look back up at the problem, it tells us that the solubility of CuBr is 2.0 times 10 to the minus 4th moles per liter. You can see that there is a 1-to-1 ratio between that reactant and that reactant, which tells us that for 2.0 times 10 to the minus 4th moles of copper bromide, we're going to make 2.0 times 10 to the minus 4th moles of copper and 2.0 times 10 to the minus 4th moles of bromine ions. So that tells us that the concentration for each of these, because we're beginning with 2.0 times 10 to the minus 4th, is 2.0 times 10 to the minus 4th, and that number can be inserted for x in both of these. Because generally you'll find, actually always you'll find, that the solubility that you're searching for, the solubility, equals x. Okay, so solubility equals x. Okay. Multiply the two x's together, that's going to give us a KSP of 4.0 times 10 to the minus 8th. 0. This constant is characteristic of copper bromide at this temperature only. If more copper bromide is added to the solution at this temperature, the product of their concentrations multiplied together, their products, must equal this KSP that we just calculated. Additionally, even though you might have noticed that I wrote units, it really is more normal to delete or to not to use units for KSP. In calculating KSP from the measured solubility, it's assumed that all of the copper bromide actually dissolves and there are no ion pairs that remain in the solution other than what we would anticipate. Also, if you are given a solubility in some units other than moles per liter, you need to change it to moles per liter. Alright, let's look at another problem. For this one, we're given a KSP value and we're asked to calculate the solubility. So again, because of this, we can start off with our law of mass action and an icebox. In this case, we have a slight difference because we have a 2 here for our coefficient. So our law of mass action is going to equal the concentration of the copper ion multiplied by the concentration of the iO3 minus, and that's going to be raised to the second power. Alright, let's take a look at our icebox. ICE here. We are ignoring our solid, which is why I'm not paying too much attention to it. We're going to start off with zeros for our initial line. We're going to add in x. In this case, we're going to add in 2x because of our coefficient. We're going to have x and 2x. The 2x goes in here. The x goes in here, which gives us an overall KSP equation of 4x cubed. Okay. Solving for x is possible because we're given a KSP of 1.4 times 10 to the minus 7th. And this is going to give us an x value of 3.3 times 10 to the minus 3rd moles per liter. Because again, our x value is our solubility. As you can imagine, these types of problems are also a great place to see the common ion effect. If one of the ions in the solution from the solid that's being dissolved already exists in the solution from some other solid, you're going to have a common ion effect present. Okay, so let's take a look at a problem for this. Calculate the solubility of the silver chromate, actually it's a silver chromate, in a 0.1 molar solution of silver nitrate. We're given the KSP value, and we're given a KSP equation, which actually I need to correct. Because if you look at it, we've got a coefficient here of 2, so there needs to be a 2 here as an exponent for the silver ion concentration. Okay, so let's take a look at our icebox real quick. We're going to have ICE, okay, but in this problem we're told that we're starting off with a certain amount of silver from the silver nitrate. Okay, so that means instead of having an initial concentration of 0, we're going to have an initial concentration of 0.1, okay, and this one starts off as 0. Our change line is going to be plus 2x because of that coefficient, plus x over here. Okay, so we're going to have 0.100 plus 2x. Okay. These equilibrium expressions, or these equilibrium concentrations, or what will ultimately be them, can then be placed back up into our law of mass action. Okay. And I'm actually going to let you solve for x in this one, and you solve for the solubility. The only difference between this and the other problems is that we began with an initial concentration of the silver because it came from the AgNO3. And that's the result of having two sources of silver ions, thus a common ion effect in this particular case. Alright, that's all we're going to talk about for now. There will be another video regarding precipitation reactions and how these concepts of solubility can be applied to double displacement reactions or single displacement reactions. But in this case, make sure you can solve some of these KSP problems, and we'll check back soon.